Memory is a crucial component that you need to understand before we actually get to programming assembly. I like to see memory as just a sheet of paper on which you draw a line. And a sheet of paper on which you draw a line will mean something, right? It will mean, for example, 1. And a sheet of paper that has nothing on it will be a 0. To me, memory is just a change in matter, and that's pretty much how the computers handle memory. If it would have to store a 1, it will send electricity to a certain component, and if it wouldn't want to store anything, it would just not send electricity. Now keep in mind that this is a really simple way of explaining it. There's obviously more to it, but you don't really have to know more than this. You'll understand these concepts later, or you can make your own research. Now, just like any other form of data, we obviously invented units of measurements for it. The smallest unit of measurement is called a bit. A bit really is just either a 1 or a 0. If you were to take 8 bits and put them together, that will make what we call a byte. And if you were to take 16 bits or 2 bytes and put them together, that will make a word. And now going even bigger, if you were to take 32 bits or 2 words and put them together, that will make a double word. And finally, if you were to take 64 bits or 2 times a double word and put them together, that will make a quad word, which is basically the biggest unit of data that you need to know. There are things called data structures in computer science which are extremely useful to us developers. As their name suggests, they are used to structure data, which makes our development extremely easier, and so also makes it easier for us to find this data. Now, there are 2 main data structures in your computer that you need to understand before you begin actually programming in assembly. These are the stack and the heap. The stack works pretty much just like a stack in the real life. Let's say you have a stack of books in the real life and you wanted to access the 3rd book in this stack. Well, you will have to remove the 2 books on top of it in order to do so. Well, the stack in computer science basically works exactly the same way. These kinds of data structures are called last in, first out data structures. That basically means that the last element to be added will be the first one to be removed if you were removing an element from it right after. And the stack is basically just an operation of a push when we add data to it and a pop when we remove data from it. And just to clarify, the stack has its own memory space to your program. When your program is created, of course it has all its own data, but it also have its own stack which will contain values that will be pushed and popped from it later. Well, you could just access the memory that's already there in your program. We use the stack as a convention, which makes operation extremely faster and simpler to perform. In your processor, there is a register called the stack pointer, and it's called that for a reason because it always points to the top of the stack. Now, there are multiple conventions of how the stack will push and pop values from it and update the stack pointer, but the one we'll focus on is called the empty stack convention. This convention will make it so that the stack pointer will of course point at the top of the stack, but instead of pointing at the value at the top of it, it will point over it at the value that's not inside of the stack. It will also make it so that when you push a value, it will first push this value to where it points and then move the stack pointer upwards. And when we will pop a value, it will move the stack pointer downwards and then remove the value that's there. Now, there's also 2 conventions of how the stack pointer will be increased or decreased when we push or pop values to it. The ascending stack will increase the stack pointer when we push values to it and decrease it when we pop values from it. And the descending stack will decrease the stack pointer when we push values to it and increase the stack pointer when we pop values from it. We'll only focus on the descending stack since it's the one most used by systems nowadays. Now, let's say we have a stack in front of us. The stack pointer is pointing somewhere in it at a value that is considered as empty. All the values under the stack pointer are considered as part of the stack. They are non-zero. And all the values over the stack pointer are considered as empty, and the value inside the position of the stack pointer is also considered as so. While the values there are not empty, they are considered by the convention as being empty. Now, just to clarify, when I say over the stack pointer is addresses that are higher than the stack pointer's address, because in my visual representation, the values that are over the stack
stack pointer are not inside of it, and that's because their address, as you can see, are smaller than the stack pointer. Now let's say we were to push 5 on the stack. 5 will be written to the stack pointer's address, and then the stack pointer will be decreased. And if we were to pop 5 from the stack, we will do the reverse. We will increase the value of the stack pointer and then just move the value that's there inside of a register. Now the value isn't overrode by zeros, we just leave it there. It's not part of the stack anymore. When we'll push a new value to the stack, it will be overwritten anyways. Now you might be wondering what the stack is for anyways. Now remember when I said that when we pop the values, they get moved to a register? Well, that's because the stack is used to store values that cannot be stored in the registers because there's not enough place temporarily in the memory. So when we need to access this value, we basically pop it so that it gets moved to a register and we can access the register. And because the stack is just memory, you can still just take the stack pointer and add an offset to it to access some values. Nothing stops you from doing that or just accessing without even using the stack pointer. Now that we understand the stack, let's understand the heap. The heap is what we call dynamic memory, because compared to the stack, which is a static memory, the heap can store as much data as your programs want. There is no limit of size that the programs can use for the heap. The only limit there is your hardware. We also say that it's dynamic memory because the heap is not ordered in any way. If your programs need to extend a certain amount of memory, it can. In the stack, if you were to put a certain size of memory, you wouldn't be able to extend it. While in the heap, you completely can without any restriction. And the heap is just used to store long time, large data that cannot be placed on the stack otherwise. In the heap, nothing is organized, and that's what gives it such power of allocating any memory any way it wants. It's finally the end of this lecture, and thanks for watching it. I'll see you in the next one, and right before we go, I just want to clarify that if you don't get these concepts really strongly for now, it's really not the end of the world, because we'll actually do practice later and you'll see that you'll understand all of them extremely good. See you in the next one.